Welcome to the APL quest. See APL Wiki for details. Today's quest is the third from the 2015 round of the APL problem solving competition. We are to generate the Farey sequence of order n. The Farey sequence is the sequence of fully reduced fractions from 0 to 1, where these fractions only consist of numerators and denominators that are between 0 and n. And they have to be given in ascending order by their value. And so we can see here an example for n equals 5. We start off with 0, which is 0 wholes, a fifth, a quarter, a third, not a half yet, because 2/5 comes in between a third and a half. And there are various ways to generate this sequence. We'll have a look at a few of them. So let's indeed start with this example of 5. And one way we can generate the sequence is by generating all the possible fractions using the numbers between 1 and 5. The 0 is a little bit special. And then we can get rid of the ones that are not what we want. So one way we can generate all these pairs of numbers that represent fractions is to think of an array of the shape 5 by 5. So all the valid indices in such an array are all the different pairings. These are all the combinations of numbers between 1 and 5. And this contains all these fractions that we are interested in, plus some that we don't want because they are invalid. So, for example, 2, 2, and 3, 3 represent the same value as 1, 1, but they're not fully reduced. And some of them are larger than 1, like 4 halves or 5 thirds, and so on. So, we start off with this. We don't need it to be a matrix, so we can start by raveling that. And then we need to figure out what quotients they represent. So if we divide, we do a division reduction, dividing the first element by the second element in each one of these, that gives us our quotients. And now we want to find out which elements are the ones that are valid and unique. We don't need duplicates. So we can see, for example, here that 1 divided by 1 gives 1, and 2 divided by 2 also gives 1. And we only want the first occurring one. That's the one that's that's fully reduced, as it uses the smallest numbers. So we can use a unique mask. This gives us exactly what we want. A Boolean vector with a 1 for the first occurrence of every value and 0 for all the duplicates, which we can then use to get the indices of the elements that we want to keep. That's one criteria. The other criteria is that the fraction represents a number that is less than or equal to 1. So we can say 1 is greater than or equal to these values, and that gives us this Boolean mask, and then we can find out the indices of the elements that we want. And so we can see that many of them are okay to begin with, but here we've got element number 6 is valid in the sense that it's not a duplicate, but it's not valid in the sense that it is less than or equal to 1. So here, third, fourth, fifth, sixth, that would be 2 wholes. That's 2, and indeed that is invalid. So what we want are just the indices that are in both groups. That is the intersection of the indices for the mask indicating which ones that are less than or equal to 1, and the unique mask. So this is the subset, the intersection of these two. And now we can use these indices to index into our quotient. So let's give our quotient the name, and then we use that to index into the quotients. That gives us just the quotients that we're after, and then we can grade that. This gives us the order that we want to put the fractions into. The fractions we generated over here. Let's give that a name. And then we want just the fractions that are by these indices that we generate over here. And we want them put into this order. And the only thing we're missing now is the 0. So we can stick that in front and have that separately. Either way we do it, we can say 0, 1 concatenated. The only problem is that we have a nested array on the right and a simple two-element vector on the left. But if we do this over the nest function makes sure that the result is nested if possible. So this is going to enclose the left but not the right. It's also known as enclose if simple. And that gives us this function that's able to run all of this. And we can even do it with 0. And that gives us just the 0 as the problem statement states. So let's give this a name. We'll call this I for we generated all the indices, and then another I because we were using indices to select the subset that we want. We can also create a very slight variation in this by making an observation that the intersection of indices between these two masks, that is, the indices where both of these masks are true. So we both want them to be that the one is greater than or equal to, and the unique. And we can actually see the relationship between this set function and the Boolean function AND. They both have the same kind of general shape, just like OR and union do. And so instead of finding the indices first, we can find the combined mask where both of them are true, and then we find the indices that are true for both of them. And such a slight variation in code can actually make quite a difference in performance, as we will see. Copying in the CMPX utility for comparing execution time, we're going to code an II on 1000 and IJ on 1000. And then we can see that we got a tremendous speed up from this very slight variation, where we just prefer to work on Boolean masks instead of working on indices. And that is in general true for APL. So we are still using indices after we use our Boolean masks. We might think that we can get even better performance by eliminating the use of indices as much as possible. So over here, where we get the indices in order to select a subset of the quotients, we could also just use the mask directly to filter the quotients. We need an indexing in order to do the sorting, but now that we don't have I anymore for the indices, we instead can use the mask to filter also the fractions. And so let's call this I using masks all together. And then we can compare the performance of our best indices type solution and the one that's using only masks. But we'll see that that doesn't really make a significant difference. So it's not always that eliminating indices and using masks are better. But for some cases, and it's good to do these performance comparisons. Okay, a different approach. Let's instead think about this in a more number theoretical way. So we are beginning with the indices from 1 to 5. And then we'll do all these combinations the same way that we generated all the combinations using iota, omega, omega. We can do an outer product using the same argument on left and right. And in here, we state our criteria for being chosen. And so what are our criteria? Well, we want our fractions to be fully reduced, and we want them to represent a number that's less than or equal to 1. So fully reduced, what does that mean? It means that they are relatively co-prime, or relatively prime. That is, there is no number that we can use that we divide the numerator and the denominator by to reduce the fraction further. That is to say that the greatest common divisor is just 1. So we don't get any further by dividing it. So that has to be true. And also, it has to be true that 1 is... it also has to be true that the number that is represented by this fraction is less than or equal to 1. And that's only true if the numerator is less than or equal to the denominator. So with this outer product, we're having numerators on the left and denominators on the right. And so we just need to make sure that the left side is less than or equal to the right side. And that gives us this Boolean matrix. And here we can go in and find directly what the pairs are with where. So these are all the ones where it is true. Now what's missing is that we need to sort them. So we can sort them in the same way as before. So we can do the division over each one of them and grade that. And this gives us the order we want to put these fractions into. All the fractions are given here. And so we sort the fractions by this. And that gives us the proper order. And the only thing that's missing, as before, is the one for 0. And we add that in exactly the same way as before. So let's call this one G for we're finding the greatest common divisor. And then there's a trick we can do here. We're having an outer product, but it's a custom outer product. It's not just using a primitive like j times and j less than or equal to. And by unrolling this into into simple outer products, then we can take advantage of optimizations in the interpreter. So what's actually happening here is we're combining two things with an AND. We have the outer product with less than or equal to, and we have the outer product with the OR. And so this is unrolled G into two outer products. And that can actually make quite a difference. So if we compare G on 1000 and G2 on 1000, we can see that that little change of unrolling the complex outer product into simple outer products gives us tremendous performance advantages. Okay. Here's an entirely different way of doing it. So far, we've been generating all these enumerators and denominators, only then to reduce with division over them all to get our quotients. What if we started by generating the quotients? So here is an outer product of the numbers themselves. So this gives us all the quotients right away. And then we can ravel that into a simple vector. And now we just need to eliminate all the invalid ones. So what does that mean? That means anything that is greater than 1 needs to be eliminated. We can do that by clamping it to 1. So we take the minimum of 1 and all these values. So we can see that the 2 now became 1, and 3 became 1 as well. 1.5 also became 1. So you get a bunch of 1s there. Then we want to get rid of the duplicates, and we can do that with unique. So here are all the quotients that we want, but they are not in the correct order yet. Now, the only thing we need to do with them is to sort them. We don't need to grade one thing and use that to reorder something else. So we can use the sort idiom, which is going to have a performance advantage as well. Now they're sorted. And we just need to transform them into their corresponding fractions. And we can do that quite cleverly because we can use the greatest common divisor on non-integers to find a number that we can divide with and still get it to be the result to be an integer. And so if we just divide by that number, that gives us our integer, and we want the greatest common divisor with 1 on each of these. And what we want to divide is both these numbers themselves and 1. So that will give us the enumerator and the denominator. So these are our fractions. And then the only thing, as always, is we need a 0 as well. Now we could stick in a 0, like we did before, just concatenating that. But since we're anyway converting to fractions, we can also just put another 0 over here on the left, and that takes care of the 0 case as well. So this is the one that uses quotients right away. Now, even here is a bit of a trick. So everything up onto the sorting looks very nice and flat. But then we have a very explicit loop. We're doing each. We're applying this derived function on each element. And we can avoid that by thinking a bit in higher rank arrays. So we still want the one on the right. But let's, instead of doing for each one of them, we generate a pair like this. Let's generate a 2-column matrix. So 1 is the right argument to this train, the fork. But we need to make this vector into a column. So we concatenate rank 0. We want every scalar in our list over here concatenated with another scalar to become a 2-element vector with a scalar 1. And that means that every cell, every major cell, and also every cell which was before a scalar becomes a vector, and the result becomes a matrix. Now we get a 2-column matrix. We can try this. And then we need to divide these rows by the corresponding greatest common divisor. So we can still do the greatest common divisor like before, and we just need to divide the rows of this matrix. So the rows have rank 1 with the scalars of the let's go. So this is upside down. The scalars of the greatest common divisor. And that gives us this matrix. And these are, in fact, our fractions with 1 fraction on each row. However, the problem statement is that it should be a vector of vectors. So the last thing we do is to split that. and that gives us our vectors of vectors. So we try to stay flat as long as possible, only changing to a nested representation at the very end. So let's call this using quotients as before, but the flat edition. And then let's compare the performance of the quotients on 1000 and the quotient flat edition on 1000. Even though it's a little bit more involved using rank over doing the each, but well, the result speaks for itself. Okay. Finally, in all these cases, we generated too much. We generated all the different combinations in order to filter them down to the ones we wanted. Maybe we can instead generate exactly the fractions that we want. And turns out that there is in fact a formula to go from an existing sub part and the leading part of the sequence to the next element. So much like Fibonacci numbers are constructed by the sum of the last two elements generated so far, so too the Farey sequence can be generated by looking at the last two elements before. So we always, every Farey sequence begins very simply. We begin with a 0, and then we begin with 1 over n, or 1/nth. That. So in our example with 5, we start with 0 whole, and then 1/5. That's always going to be the smallest possible fraction. And then if we look at, or you can name our fractions in sequence. So the next to last one that we have so far will be a bth, or a over b, and then last one we have so far is c over d. And then the next one coming up is p over q. And these p's and q's can be computed with a not too difficult formula, just in terms of a, b, c, and d, and the n, which is the type of sequence that we are generating right now. And so we can do that right from the start. We know that the first two elements have a equals 0, and b equals 1, and c equals 1, and d equals n. And that allows us to compute the next term, the third one, and then the fourth one, and so on until we're done. And the stop condition for the sequence would then be when they are the same, when we've reached one whole. So let's try to state this. It's going to be a bit verbose, but it's not really very complicated in itself. So first we want to generate the start sequence. Let's say for 5. So we know that the first one is going to be 0, 1, because it's always 0, 1. And the second one is going to be 1 and n, which is our argument here. Now since this is what we're starting with, and then we're going to add more elements, there's one issue, which is when n is 0, then we don't want to have the 1 and n. That would give us 1/0. So we want to eliminate the second element, only take the first element of this when n is 0. So what we can do is we can take how many elements from this? Well, there are only 2, and we want to, or we can drop the last one when n is 0, or we can add 1 to n. So for 0, this gives us 1, and for 1, this gives us 2, and for any number higher than 1, that gives us more than 2, and then we can clamp that down to 2 by taking the minimum. So for 5, this will give us 2, and for every number it will give us 2, except for 0, where it will give us 1. So this is one way to restrict it like that. And then we want to apply the transformation over and over again until our stop condition is met. So we're going to write the transformation eventually. Let's just put in the stop condition. So we use the power operator for that. And we want to continue applying this transformation of adding one more element to our sequence, one more fraction to our sequence of fractions, until what we have generated, the last element, it is true that the fraction is finished. So it is the last one. So it should be 1 over 1, or we could even say if it's more than that, if it becomes positive, then we are also long finished. So if the enumerator is greater than or equal to the denominator, then we're done. Now, there's yet another problem. The power operator will always apply the function at least once. But what if our n is 0? In that case, we don't want it to apply at all. So this derived function, which is an apply until a certain condition is fulfilled, we can say we want to apply this either once or no times, depending on whether we have n equals 0 or not. So we want to apply it once if n is greater than, it's not even just 1, not even just 0. For 0 we don't want to apply it at all. For 1 we also don't want to apply it because we already have the full sequence, 0 and 1. So for any number that is greater than 1, this evaluates to 1, and then we apply this whole derived functions once. And for 0 and 1, this evaluates to 0, and we don't apply this function at all. And that gives us our sequence that we want. This is an array. This is also an array, so we just need to separate the two of them. Okay, and now for translation of this whole sequence, we also have to remember that in that formula that we had, you can go back and look at it for a moment. We are using the last 2 elements of the sequence, and we're using n itself. So n itself, that was the right argument here. We're feeding it in as a constant left argument to this transformation function. Then we take the last 2 elements of the sequence that we've generated so far, and then let's pick that apart into these names A, B, C, and D. So A and B is the second to last fraction, and C and D is the last fraction. So we are unpacking that. And then we just need to translate all the mathematics, and that's pretty much a mechanical translation. So we take n plus b goes the formula, and then we're dividing that by d. We need to round that off and multiply c and d by that, and then we need to subtract a and b, and that gives us our new term in the sequence. So we can take the existing sequence and concatenate this new element to that. So we run it, and we got the sequence that we want. So we generated just the fractions that we were after without generating anything else, just in order by computing the next term in terms of the terms that we already have created. So let's call this P for power. We're using power to iterate over it. And then we'll make one little enhancement to this for performance sake. Because here, we were again dealing with nested arrays. We started off with a two-element vector of vectors that's already nested, and then we kept appending more nested elements to that. And we should really avoid doing so as much as possible. So let's try again to generate this two-column matrix that we saw before. And then only as a very last step, split that into vectors of vectors. And so we want these four numbers in a matrix 2 by 2. However, if so we can reshape that. You could reshape it into 2 by 2. However, if our n is 0, then we want it to be a 1 by 2. We only want the very first ones as a single row matrix. So we can use that same formula as before. We can clamp 2 with 1 plus omega, and that gives us, in all other cases than 0, it will give us a 2, and then for the 0 case, it gives us a 1. And now we have a 2 by 2 matrix, and we're going to add more rows to this. And so all the conditions, everything is the same. Here, we were looking at the last element. We don't want to use the last element anymore. Now we want to use the last major cell. Other than that, it stays the same. And the formula here is all the same. Instead of concatenating an enclosure, we just do a leading axis concatenation. We add one more row. And over here, where omega is a matrix with two columns, negative 2 take will give us a 2 by 2 matrix again. We can just ravel that and assign to all these four names in a flat way. So this is the same power-based solution, but the flat addition. And then we have to remember to split at the end so that we get a result that is a vector of vectors. We can try this on 5 and see whether you get exactly the same result. So ever so slight variation to make it use flat arrays as long as possible. How does the performance compare? We have P, and I'm not going to run it on 1000 because I happen to know already that this is not a fast approach in APL. So let's just do it on 100. And we can see that staying flat as long as possible was a really good idea. That saves us a lot of performance. But on the other hand, we can see that if you compare to the queue that we have above, that they don't, the way we were doing is for 1000 instead of 100, it doesn't look very promising. And let's take the best of every category and pit them against each other. So, and we'll just do it with 100 this time. So the best we had was with using indices. We wanted to use the mask. Whether we use the mask all the way through or whether we only use the mask initially to select which elements was not very important. But we can use the one that uses the mask. That was the one that had best performance. Then we had the version that used the greatest common divisor, and we found that by splitting our outer product into two outer products, we got significant performance improvement. Then we had the solution that did the quotients right away, and of course staying flat was a good idea. And finally, we have the power approach, where we keep extending our sequence, and again the flat one was the fastest one. Let's compare all of these. And so we can see that computing the quotients was indeed the fastest way by far, although using the two outer products with the number theory, the greatest common divisor, was not a bad approach either. Thank you for watching.